Hey everyone, and thanks for tuning in again. Today's video will be about checking regression assumptions. So I'll be showing some approaches I use for checking assumptions, and remember, out of the Gauss-Markov +1 assumptions, only 3 can be tested with sample data, and these include homoscedasticity, independence of errors, and normality of errors. The approach I'll be showing is a quick and informal screening. So this is what I call my first line of defense. So in every data set, most assumptions are typically already violated to some degree. So the goal is really to see if it's bad enough to warrant further actions. So the main question is, does the evidence suggest that I need to worry about the results of my analysis being affected? So remember, when some of these assumptions are violated, it could bias our estimates, and it could also change, it could upwardly bias or downwardly bias our standard errors, therefore affecting statistical tests. And we don't want that to happen. So if the evidence does show that I need to worry about the results of my analysis being affected, I can follow up with more formal tests, which will be covered in other videos, the diagnostic videos. But if not, then I could just proceed with my analysis as usual. So there are many approaches and sets of approaches for assumption checking, and this is just what works for me. So ultimately, you can take and run with what works for you, and you can drop what doesn't. Assumption checking, whether formal or informal, are simply rules of thumb, which are usually not generalizable to all situations. So none of the rules that I talk about here are set in stone, and they change on a case-by-case basis. Sometimes, not all the experts even agree on what the rules of thumb should be. So the purpose of assumption checking is to build a compelling case that either shows that assumption violations will not affect the outcome of analysis or are not likely to affect the outcome of analysis, or that assumption violations have been addressed to an extent that the outcome of the analysis will no longer be affected. So again, the approach I show here is how I begin to gather evidence to build my case and many times I'm talking about reviewers, my case for reviewers. So there may be a bit of overlap in this video with the regression diagnostics videos, but again, this is just a quick check, mostly based on visual inspection of graphs and plots. More formal statistical approaches for detecting assumption violations will be covered in the videos on regression diagnostics. So with that, let's go ahead and get started. Okay, so what I have here is I've opened SAS, and I've opened up this file called week7_template SAS. And just like we've seen before, I've used comments to create these headers that will ultimately organize our code that we'll be writing. So this template is available online if you'd like to use it, and if not, it's totally fine. You can organize your code in whichever way you choose. Alright, so the first thing we're going to do here is we're going to read in the data. There's a new tab delimited file, a .dat file called regdata3.dat, and we're going to go ahead and import that. I'm going to import data. It's a tab delimited file. I'm going to find where the dataset is, so I put my dataset on the C drive in the datasets folder. And again, nothing shows up because it's limiting it to .txt files, and our file is a .dat file. So I'll switch that to all files. And then here it is, regdata3.dat, or it's a DAT file. I'll go ahead and click open. Next, remember this is what our data set will be called, so I want to call it regdata3. And then we can just go ahead and click finish here. Alright, it says 150 rows were created, and there are 150 observations in the dataset, and there's 5 variables. So if we go into libraries, into the work folder, we can click on regdata3. So we have 150 observations, and we have x1 and x2, and then y1, y2, and y3. So the way that I've generated this data, we have the predictors, x1 and x2, and then the criterion variables, y1, y2, and y3. But these are all meant to be part of separate regression models. or separate regression analyses, where x1 is paired with y1, x2 is paired with y2, and then y3 is just a standalone criterion variable with no predictors. But I put them all into one data set so we could take a look at all of the variables simultaneously. Okay, so I'm going to go ahead and click out of this. Our data set looks good. And then remember, the first thing that we want to do is we want to set our output delivery system, or our ODS, to HTML. So I'll go ahead and run that to start. And then here, remember that these lines, the save until the end, and then ODS RTF path, and then these last 3 lines, or actually these last 2 lines, these lines are for exporting your output to a Word document at the end when everything is done. So when you're done with the lab, or you're done with typing out all of the code for your analyses, you can just backspace here. Remember, it's just this line, and then you would want to backspace on the quit, and then the ODS RTF close. And then if you were just to highlight the whole thing with all of the code in between, it will export all of your output to a separate Word document. And remember, here you specify the location of where you want that document to end up. And then here you want to specify what you want the Word document to be called. So in this case, I've named it Week 7 Lab. But for now, I'll go ahead and comment that line out. And so first we'll start with descriptive statistics. And we're going to be using a different function. We've been using proc means. But for this, to be able to get skew and kurtosis values, which is what I want to start with, I'm going to use proc univariate. And so our data set is reg data 3. And then I want the descriptive statistics for all of my variables, so I could just I could just type in run, and then we can go ahead and run this. All right, so there's going to be a lot of stuff here that we don't need. But we have all of our descriptives, so our mean, standard deviations, especially if you're working with a data set that you're familiar with, the minimum and maximum can really be helpful in seeing if there were any input errors or just anything that's out of bounds. So we have some extreme observations here in this little table, and that's really helpful. All right, so what we want to focus on are the kurtosis and skewness values. And so as a rule of thumb, and not everyone will agree with this, but plus or minus 3. So if there's anything less than minus 3 or anything above positive 3, that would be cause for concern. But in my own work, personally with simulation studies that I've done looking at skewness, anything over about 1.2, 1.1 tends to create a variable that looks pretty positively skewed. Again, those are just rules of thumb, but what we're doing here is we're just doing a quick sweep of the skewness and kurtosis values so we can take a look at the variables that may be problematic later. So we're just taking mental notes here. So here, nothing really close to the values that I said, nothing plus or minus 3 for kurtosis, and then nothing even close to 1 or greater than 1 for skewness, so that's fine. Nothing here. And again, remember, even though I'm checking these, for x1 and x2 I don't have to, because the normality assumption is not on the predictors, but it's on the outcome variables. And even then, the actual assumption is on the residuals, but we focus on the outcome variables because those are a good proxy to what the residuals, or how the residuals will be distributed. So remember, the predictor variables, we don't really care about what those distributions look like. We're more interested in what the outcomes look like. So y1, y2, and y3. So when we move to y1, Skewness and kurtosis, that looks good. That's not less than -3 or greater than +3, and that's not either. And then when we move to Y2, skewness is a little bit higher, so we might want to take a look at that. And kurtosis is also a little bit higher, so that's greater than +3, so we might want to take a look at Y2. And then here, skewness is a little high, or higher relatively, so we might want to take a look at that, but skewness seems to be fine, or kurtosis seems to be fine. All right, so just taking a mental note, we'll want to take a look at Y2 and Y3 a little bit closer. Okay, so that's those are the descriptives. What we're going to do next is we're going to look at our first assumption, or the first assumption that we can test in our sample data. So that's assumption 3, which is homoskedasticity. And again, what we're looking for here is that the variance of, so what we're really interested in is the variance of the residuals, but we're going to use y as a proxy to the residuals. So we want to make sure that the variance of the residuals on y are that the variance is equal across different values of x. And that will make more sense once we produce our scatter plot matrix here. So what we've been doing before is we've been making scatter plots, but what I'm going to do here is make a scatter plot matrix, which is very similar to a correlation matrix. And so I'm going to use proc sg scatter, and then the data set is reg data 3. I'm going to give the scatter plot matrix a title, scatter plot matrix, and then with the matrix statement, we'll type out the variable names. And in this case, I want to see all of the variables in the scatter plot matrix. And then we can go ahead and run. We'll just give it a second to output here. Okay. So the way that you read this is you just look at, whenever you find a plot, you just look at what variables intersect at that plot. So if I want to look at x1 and y1, that would be this plot right here. And then if I want to look at x2 and y2, that would be this plot right here. And so again, what we're looking at is it's based off of what's the criterion, what's the predictor in the model that you're interested in. And so we don't have to look, in this case, we don't really care about how x1 and x2 are related on the scatter plot. That's not what we're focused on right now for this assumption. What we want to look at is how the predictor and the outcome are going to be distributed. So for example, like I said, y1 and x1 are part of one model, so we could look at it. This is the scatter plot here, and then you get the scatter plot reflected over here. So x1 and y1. And then x2 and y2 here, and then you get it reflected over here. So as you can see, this is just this one, where x2 and y2 is just a reflection or a rotation of this plot here. Okay, so when we look at x1 and y1, this is an indication, this indicates here that there may be a violation to the homoskedasticity assumption. Because as we get from, on the left side, our lower values of x1, and on the right side, our greater values of x1, and as we get from less to greater, or as we move from one side to the other, the variance in y seems to change. So as y is more tightly clustered at the lower end of x1, it is not as tightly clustered and more spread out here at greater values of x1. What we call this is a megaphone shape. And a megaphone shape is indicative of a violation to homoskedasticity. So again, as the values of x1 increase, the variance of y, which is a proxy to the variance of the residuals, it also seems to be increasing. So it is not equal at the different values of x. Okay, so like, what do we want to see? So if you look at here, x1 and y2, although those variables are not from the same model, or the same model that we're interested in, this is more of what you want to see in the scatter plot. That as you go across the predictor variable, the variance of the outcome seems to stay the same, and that's more of what we want to see. So looking at the scatter plot matrix, we can start to gather some evidence for variables that for predictor and criterion relationships that are violating the assumption of homoscedasticity. All right. So next, what we're going to look at is assumption 4, independent errors. And the way that we'll take a look at that is we'll plot the predictor against the model implied residuals. So this is given to us automatically by those plots that we would get in earlier labs, where when you would run a regression model, we would get a bunch of plots. I don't know if you remember that, but one of those plots is the predictor plotted against the model implied residuals. So we'll get to take a look at that. And then something else that we'll do is we'll save our residuals so we can take a look at the distribution of the residuals later on when we move on to assumption 6, normality or normally distributed errors. All right. So we're going to go ahead and use proc-reg to run our regression model. Our data set is regdata3. And then we're going to go ahead and type in our model statement where y2, or the example model we're going to use here is x2 predicting y2. And then just as we have before, we'll type stb so we can get our standardized coefficients just in case we need them later. And then this is the new part. So I'm going to use the output statement, and then so to save the residuals, we're going to create a new data set, and that data set is what we put here in the out equals. And so the new data set, I want to call it regdata3b. And then I'm going to enter one more time, and then I want to save the residuals. So R, this capital R, is indicating that I want to save the residuals, and I want to save them under the name resid, R-E-S-I-D. So I'm giving it that name. So again, you have to type out equals, and then you can give the new data set whatever name you want. Just make sure it's different from the original data set so that you don't lose the original data set. And then this R equals is also required for you to type, but the resid, that's what you decide you want to name the residuals. So you can name it whatever you want. So there will be a new data set, regdata3b, that has all of the variables in our original data set. So it'll have x1, x2, y1, y2, and y3. In addition to the residuals. All right. And then we can go ahead and run this. So here's the regression. We have the ANOVA table and the coefficients like we've been getting in other labs. But right now we're just focused on this plot right here. So this is plotting the residuals from the model against our predictor, which is x2. And so looking at this, if errors are independent, then there should be no pattern in the points here. But as you can see, there's a bit of a U shape here. and that's indicative of a violation of the independent errors assumption. And so that's another thing that we want to take note of as we move forward, is that in regards to the model for x2 predicting y2, there's a potential violation of the independent errors assumption. And we can see that because there's a pattern in the scatter plot between the residuals and the predictor. Okay. So we're going to go ahead and move on to assumption 6, which is normally distributed errors. And just as we did in homoscedasticity, we're going to be using the distributions of the outcome or the criterion variables as a proxy to what the distribution of the residuals would be like. So remember that when we ran our descriptive statistics using proc univariate, y2 and y3 had values of skew and kurtosis that were a bit high relatively. So we're going to go ahead and take a look at those variables in particular. So to get our histograms, we're going to use proc univariate. Our data set is reg data 3. And then in the var statement, we can type in the variables that we're interested in. So I'm interested in looking at y2 and y3. We're going to state that we want histograms, and then we can run. And if you were to take this histogram line and put it up here, it would be doing the same thing. But I just want to have this organized in terms of the assumptions that we're looking at. So I'm going to go ahead and run this for y2 and y3. Again, we're going to get a lot of stuff that we don't need because we already looked at our descriptive statistics earlier. But here we have variable y2, and here's the histogram. So it does look a bit positively skewed because the tail is kind of leading off to the right here, but it doesn't look too bad by visual inspection. I mean, it looks pretty normal except for this, this lingering point over here. And then for y3, this looks to be a bit more positively skewed. It doesn't have, so as in y2, it kind of trails off on the left and on the right, making it look more normal, but here it doesn't really trail off to the left as much as it does to the right. So this might be indicating that it's a little bit more positively skewed. So again, our assumptions are always usually violated. Normality is often violated, but it takes a really, really large degree of non-normality to affect the results of an analysis. So although these distributions are a bit positively skewed, it might not be enough. It might not be enough of a violation for us to have to worry about it. And so that's why in later videos we'll be going over how to run more formal tests of assumption violations, which are also known as regression diagnostics. Here we're just doing a quick check to see if there's anything that we should be concerned about. So later on, we'll want to make sure that we take a look at y3 and y2 a little bit more closely because of these clues that are suggesting non-normality or violations to the normality assumption. Okay, and then the last thing here is we're going to use proc univariate again. And I just want to show the histogram of the residuals from our model that predicts y2 from x2. And so remember, so I'm going to pause right here with typing out the syntax. And if we go here to Explorer, you can see we have this new data set, reg data 3b. It may not open, so I wouldn't try opening it, but it is there. And so from that data set, so here data equals, I'm going to type reg data 3b, and then the variable that I want to plot, or the variable that I want a histogram of, is the residuals. And remember that we named that variable resid. I'm going to request a histogram again, and then I'm going to go ahead and run it. And I'm doing this partly to show that y does serve as a pretty good proxy as to the distribution of the residuals. So let's go ahead and run this. Okay, so here's our histogram of the residuals, and as you can see, it is kind of normal, or it's positively skewed overall, but it looks like it's pretty normal with this lingering point out here. And if we scroll back up to y2, it's kind of the same. So pretty similar. And so again, another indication that we have violated this assumption of normally distributed residuals. Okay, so what we've gone through in this video, we ran our descriptive statistics to get a sense of skewness and kurtosis, and then we looked at assumption 3, which is homoskedasticity, and we found some evidence for violations to that assumption of homoskedasticity. So the variance of y seemed to be changing depending on the value of x, and for the megaphone shape example, as x increased, the variance of y seemed to be increasing as well. So it wasn't equal across the different values of x. We also looked at assumption 4, which is independent errors. And given the scatter plot of the residuals with the predictor, we saw that there may be a pattern left over there with the scatter plot. So that's indicative of a violation of the independent errors assumption. And then finally, we looked at assumption 6, which is normally distributed errors. And given the distribution of the criterion variables, y2 and y3, and the distribution of the residuals for the model predicting y2 from x2, we saw that there are, it is suggestive of a bit of non-normality, in this case positively skewed variables. And so if there is cause for concern when you're doing this, remember, this is just a quick check to see if there is anything to worry about, and if there are clues that some of these assumptions have been violated, we'd want to follow up with more formal tests of assumption violations. And so I'll be covering that in future videos that look at diagnostic plots and diagnostic measures. And so with that, that concludes this video on checking assumptions, checking regression assumptions in SAS.